Okay, so in the last video we took a look at constant forces. Now we're going to go ahead and take a look at what happens if you have position-dependent forces. And that will give rise to our ideas of energy. So we will require that the force still be independent of velocity or time. So now our Newton's second law becomes F of x alone equals mx double dot. Now there may still be an implicit dependence on, say, time or something like that, but there is no explicit time dependence. Now, in general, solving these things can be a bit of a bear, but there is a little trick that you can do that makes life go a little easier. If we think carefully about what x double dot means, one way we can write that is as dx dot dt. Now, it's perfectly legal for me to go ahead and write that as dx dot dx, dx, whoops, no dot there, dx dt. Perfectly good. So I can rewrite this as v, and then this x dot here is v, so that becomes dv dx. Turns out to be a darn handy trick, and one that we'll keep exploiting. So we can rewrite our Newton's second law as f of x equals m, and then we can write v dv dx. Now what this does do ultimately is it relates the velocity to the position. So getting the time behavior out can be a little tricky if you need that, but at least it's a good start. Okay, so with that in mind, let's go ahead and define the kinetic energy. Now this text uses T. You may have been used to seeing K. Books are pretty evenly split between T and K. I'll follow your text here. We'll define it to be 1/2 mv squared. Again, we're working non-relativistically here. So let's think about what happens when we differentiate this T with respect to x. Let's just hold our nose and do it. So we'll get dt dx equals 1/2 m. Those are all constants. And I'll need to differentiate v squared with respect to x. Okay, let's do that. That gives me 1/2 m. And then, so differentiating this brings down a 2, 2v, and then I have to differentiate what's inside, dv dx, cancel, cancel. So, hey, that's kind of cool, because if we look back at our acceleration, v dv dx, here we have again v dv dx, and we got an m here, so we realize that that's ma. So this means that we can identify our force as a function of position to be the position derivative of the kinetic energy. So we can go ahead and think about integrating this. So we would integrate f of x with respect to dx. We'd be doing that from some initial position, x naught, to some final. And we'll define that to be the work, because it'll show up enough that it'll be worth it to us to do that. Now, what do we have left on the other side? Well, on the other side, once I move the dx around, I just have a dt left. So I have to integrate that from t naught to t. So this left-hand side, which I can't take any further without explicit knowledge of the force law. So we'll just call it the work. we identify that the work is equal to the change in the kinetic energy. And so that is the work energy theorem. That we had from before. Okay. Now, if we go and take a look, though, at this form here, it would be really spiffy if we could say define this in terms of some derivative of something that depends on x. So let's go ahead and do that. So we'll define our potential energy. Now, this book uses V. A lot of books use U. Again, it's about a 50-50 split. I'm following your book's notation here. We define it to be the V of x such that minus dV dx of x is equal to our f of x. Now, why the minus sign? We'll see in just a moment. But just something to note here. We actually have some freedom in choosing what our v of x is equal to. We can have an arbitrary additive constant. You can make it whatever you like, but however, once you've made that choice, you're stuck with it. So make sure it's a choice that's convenient for the problem. Okay, so we can take this and follow it along. So we'll have, oops. So we'll have f of x dx equals minus dv as a function of x. All right, and we really do want this potential energy to just be a function of the position alone and not care about the actual path we took to get there. So all right, if we integrate both sides, this goes x naught to x. This will go v of x naught to v of x. Sorry about the clutter there. And we know from before that that has to equal T minus T naught from the work energy theorem. So evaluating this, I wind up with minus V of x minus a minus V of x naught equals T minus T naught. Okay, so minus a minus is a plus, and if I rearrange this a bit, I get T naught plus V of x naught equals T plus V of x. And since this depends only on the positions and not on the path, it's got to be true anywhere as long as our force only depends on the position and nothing else. So we define the sum of those to be E, the total energy. And so as long as our force is only a function of position, the total energy is a constant. Now, it may not seem immediately obvious, but this does at least allow us to relate velocity to position. We can at least formally integrate this. So we'll exploit that t plus v of x equals E. Then we'll assume we know E somehow, initial conditions or something. So the kinetic energy is 1/2 mv squared plus our v of x. That equals E. So now what we'll do is we'll solve this formally for v. So v will equal plus or minus, because we're going to be taking a square root, and we'll have to use other conditions to know which branch to take, 2 over m times E minus v of x. Now, this, keep in mind, is x dot, or dx t. So in principle, if not in practice, we can rearrange this to get dt all on one side all by itself. On the other side, we have dx over plus or minus the square root of 2 over m e minus v of x. And all you gotta do is, well, we'll integrate that from t naught to t. And then for the little trickier bit, you have to integrate that from x naught to x. And in general, that is a bear. But in principle, you can solve anything if you can write the energy function. So we're just left with t minus t naught on the left-hand side, and that same integral on the right-hand side. And that's as far as you can take it. But we can at least think about it a little bit. And again, we've got the same issue here, that this root is in danger of going imaginary. The only way that we can have the root be real is if v of x is less than or equal to the total mechanical energy. And it generally will better be the case that v of x can never be greater than the total mechanical energy, because then the root goes imaginary, and I don't know what that means. So let's think about a typical v of x of some sort. So we'll assume that maybe it looks something like that. All right. Now let's say that our total mechanical energy E looks something like that. So what this means is that if my value of x is anywhere in these cross-hatched regions, well, I actually just can't be there. These are forbidden regions. And this makes some sense because as I move along, say I get to here, if the potential energy is equal to the total mechanical energy, it means the kinetic energy is 0. So it can't move past this point. In fact, all it can do is churn around. So we call these points right here the churning points. Of the system. So what this means is the object is constrained to oscillate, maybe not simple harmonic motion, but it's constrained to oscillate between these two x values. And so just for completeness sake, green means go. This region here is called the allowed region. So this is the purple here is the forbidden region, the green is the allowed region, the boundary are the churning points. So just by looking at this, realizing we can't go imaginary and having to explain why that would be, we get a constraint on our motion, and even without knowing the specific details of the potential energy function other than some general bit about its shape, we can say roughly what it's doing, that it has to be oscillating back and forth here. When we're right here, our potential energy is a minimum, so our kinetic energy would be a maximum, so we'd be going fastest at this point. Slow down, slow down, slow down, turn around, go back, speed up, speed up, speed up, slow down, slow down, slow down, slow down, turn around, speed up, speed up, speed up, and so forth, back and forth forever. So that's the general case. I mean, there is, if you're going to be really fussy about it, if you're right at the minimum and you happen to have v equals 0, and you're right at the minimum, then you're just stuck. So a point like that gets the name point of stable equilibrium. All right, let's take a look at a couple other cases, hopefully a little less complicated than this. So, next one I can think of, there's my V, there's my X. Let's make it look like some sort of typical molecule. There, that's pretty good. And one of the things that can happen in a molecule is a process called photodissociation. If a molecule absorbs just the right kind of photon, it can jump up to a higher energy state. So let's say that the energy is like that. Okay. Well, this spot right here is still a stable equilibrium point. So what that means is if I had it here and I nudged it a little bit, it would oscillate around here. But what if I nudged it a lot? Well, it would depend which way I nudged it. If I nudged it a lot to the left and raised its energy all the way up to here, it would come up to here. So that is still a turning point. Turn around and go back and fly out forever. If I nudged it so its energy got up to here and to the right, it would just fly out forever. But either way, it'll leave the system. Another case is, say, V, X, looking something like that. And look at this. This point right here is what we call a point of unstable equilibrium. So the reason it gets that name is, let's think what happens if I place it right here with absolute perfection and I don't breathe, it will stay there. But if I place it just the slightest bit off, or I go ahead and I place it down with just the slightest bit of speed, it will head off one way or the other forever, because as we go off to the right, let's say potential energy goes down, meaning that kinetic energy will go up and we just go rightward forever. If I shove it off to the left, same problem, we run way leftward forever. Okay, so let's finish off this video doing a few examples just to get some feel for it. So let's look at our stability a little more carefully. Oops. So in this example here, I'm going to imagine putting a cube and balancing it on a cylinder. So this is just supposed to be pushed off a very small angle. If I push it off a very small angle, you won't be able to really read what I'm doing, so just bear with me. So here's my cylinder. We'll put my origin right there. And nominally, I would have had my cube sitting perfectly on here, but let's say I put it just off to the side a little bit. Just barely. So we're just barely off a little bit, and we're off by some angle theta. Well, okay. Let's go ahead and call this radius r. So I had it placed perfectly on, and then I tilted it over just a little bit. And now we're off by this little angle theta here. All right, so radius r. And let's just say that the half height of the cube, convenient as anything, well, now let's make it blue. We'll say that the half height of my cube, like so, is b. All right, and so here's my center of mass. Now it's been disturbed a bit. So to find the center of mass, I have to go in 2 steps. First, I will be over the distance b here, and then, sorry, distance r here, and then I will be going up a distance b cos theta there, and then my upward journey ends here with an r theta sine theta here, because the arc length here is r, this distance here is r theta, right there. Okay, so my total height, h here, is equal to r plus b cos theta. So that's the y component for this little leg of it, but then I overshot, so I have to come back to the center of mass. So that'll be plus r theta sine theta, like that. Okay. So with that, then we can go ahead and write the potential energy of the system. The potential energy is mgh. Okay, let's write it more complicated. mg r plus b cos theta plus r theta sine theta, like so. All right. Now, we know that to have a point of equilibrium, you're at an extremum. So to be at an extremum, we will be requiring that dv d theta be set equal to 0 at our extremum. Okay. So again, mg. All right, let's go ahead and differentiate this through. So derivative cosine is minus the sine. So I'll get a minus r sine theta minus b sine theta. Bear with me while I wrote that in 2 terms. This one here is going to give me 2 more terms. So r is a constant, but I can differentiate with respect to theta, so I'll have a plus r sine theta, then derivative sine is cosine, so that will be plus r theta cosine theta. Okay. Thank God for small favors. Cancel, cancel. All right. So now we need to sit and think, where is this going to vanish? And there's only one place where this will vanish, and it's for theta equals 0. If that's the case, sine of 0 is 0, and cosine of 0 is 1, but I got a 0 here from the theta itself, so that works. Okay, I don't think it was any great shocker that if I sit the cube perfectly on top of the cylinder, that it's an equilibrium point. But now let's test the stability. For the stability, well, let's go back to our curves here. You can see here where it's a point of stable equilibrium, it holds water, so that would be positive curvature. And here we spill water, so that would be negative curvature. So we'll go ahead and do the second derivative test for our stability. So that would be d squared v d theta squared, and we will set that at theta equals 0. Okay, so I've got an mg everywhere. Awesome, not really going to matter. looking at the rest of this, okay, I've got a minus b sine theta. B is a constant derivative. Sine is cosine. So I will have a minus b cos theta from there. R is a constant, differentiate with respect to theta, gives me a plus r cos theta, and then differentiate with respect to theta over here is going to give me derivative cosine minus sine minus r theta sine theta. And we need to evaluate all that at theta equals 0. Okay, so at theta equals 0, all the cosines are 1, all the sines are 0, and the theta itself is 0. So we get that our second derivative is equal to mg times r minus b. So what we get is if the half height of the block is less than the radius of the cylinder, then it's actually a stable equilibrium and will right itself. On the other hand, if the half height of the block is bigger, then it will fall over. You can amuse yourself by trying this at home. You can use a sugar cube and you can try putting it on top of a soup can. That'll give you positive stability, and on top of a pencil, which should give you negative stability unless you've got a really fat pencil. Okay. One of the favorite go-to problems in mechanics is the Atwood's machine, and we will be visiting it many times. Atwood was an interesting fella. He was what was called a demonstrator, which used to be a faculty position about 120, 130 years ago. And his whole job was to develop demonstrations that could be used effectively for teaching. And what he came up with was a pulley from which he hung 2 blocks. So we'll make this the lighter one, M1. That'll be the heavier one, M2, like that. Okay. Now this problem is really neat because it turns out that you can analyze this pretty much equally effectively using any of at least a half a dozen different techniques. Now we'll start out by assuming that we have a massless, frictionless pulley. Don't worry, we'll relax those ideas later. And we'll just go ahead and assume that we're letting these go from rest. V2 naught equals 0. Sometime later, they will have moved. Now, they're under a constraint. Whatever V1 is, that's what V2 has to be. The only difference is the direction. Okay. So one way we could do this is to do it by force analysis. So let's go ahead and do that. So we'll do our force identification diagram. Okay. So for our first free body here, we cut through the string, so we have a force of tension pointing up, and we have a force of gravity pointing down. That's a long-range force, so we'll call that FG1. And then we can do the same thing for free body number 2. We'll have a force of tension up and a force of gravity down. Now these two tensions are equal. They're not strictly a third law pair. They're what we say is a pair of forces that act as if they were third law. So what do I mean by that? Well, if we follow molecule by molecule all the way around here, we can build a whole chain of action-reaction pairs such that we can demonstrate that these two have to be equal. Let me just go ahead and take a quick aside on that. So here's my quick aside. So if we zoom way in, we'll just look at a few small bits of the string as we go along. Okay, so we'll have a tension force down, and then this guy has to exert a tension force that way. Actually, let's get rid of those dots there. It'll make it easier to visualize. Okay, so this guy will be exerting a tension force here. Tension, 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 like so as we go around. Now, call this T1, T2. Now these two are an action-reaction pair. Similarly, T3, T3, those are an action-reaction pair. T4, and so forth. Now all we got to do is demonstrate the equality. The way you demonstrate the equality is you realize that that the pulley has to be pushing on this little piece of matter right here in order to balance the forces. Ditto here, ditto here. And if we look at we go ahead and construct a force triangle. Let's say we'll look at this guy here. We'll end up with T1 down. Now I'll add my normal force there. Then I have to add in my T2, and this has to close out to 0. Now, by the symmetry of the situation, these two angles have to be equal, which forces T1 and T2 to be numerically equal. So here, this T1 and T2 are actually equal by the second law. Then these T2s are equal by the third law, equality by the second law, equality by the third law, equality by the second law, and so forth as we work our way around. So the upshot as we work our way all the way around is these two forces are equal, not purely by the third law, but by a rather complicated collection of second and third law pairs. Okay. So anyway, with all of that, we've got tension up, gravity down, tension up, gravity down. And it will probably make sense for us to choose up to be positive for M1, down to be positive for M2. We're allowed to do that. So we'll have T minus M1G equals M1A. And then we'll have M2G minus T equals M2A. Now, the way I can get rid of the unknown tension that I'm not really all that interested in is I can add the two equations that will cancel the t's between them. So I will be left with M2 minus M1 G here, and M2 plus M1 A there. So we get that our acceleration A, or if we prefer, x double dot, will be equal to M2 minus M1 over M2 plus M1 G. All right. And from there, we can go ahead and get our final speed. We can go ahead and use the missing t equation from the kinematics that we worked out before. So we get that, say, v1 squared, and that'd be the same difference as v2 squared, minus v naught, which is 0. So v1 squared equals v2 squared equals 2ah, and we know what a is. So this is 2 times m2 minus m1 over m2 plus m1 gh. And then to get v, we can just go ahead and take the square root. So v1 equals v2 equals root 2 m2 minus m1 over m2 plus m1 GH. Now the genius of Atwood's machine is that we can solve this a half a dozen different ways easily. So let's do this by the work energy theorem. GY. So we're going to solve exactly the same thing. So here we'll compute the work energy theorem. So for mass 1, we can say that the kinetic energy of object 1 minus its initial plus V1 located at height plus h minus V1 0 equals the work done by tension on block 1. And we can write an incredibly similar expression for M2. Except here we will have dropped, so the position is going to be minus h minus V2 of 0 equals work 2 done by tension. All right, again, let's go for the low-hanging fruit here, shall we? We're letting it go from rest. Initial kinetic energies are 0. We may as well set our potential energy to be 0 at the beginning. No reason not to. That'll just make things go a little easier. Now, these two here have to be negatives of each other by the third law. So if I add the equations, I will get T1 plus T2 plus V1 plus H plus V2 minus H equals, well, 0. Now, actually, as an aside, we could, if we were even more clever, we could have just basically started right here. You see, I was still treating this like this was two separate systems, but I could have chosen instead to make the whole stinking thing my system. If I'd done that, the tension in my massless strings would have been an internal force, and only external forces can do work, and I wouldn't have had to think about the work at all. I mean, I never bothered computing it, but I wouldn't have had to even think about it. So, just a shout out for cleverness. So, anyway, this would give us 1/2 m1. Now, these are constrained to have the same final speed, so we'll just say v squared plus 1/2 m2 v squared. We know the gravitational potential energy of the first object will be m1 gh. The second will be, because it's a negative h, we'll have minus m2 gh equals 0. And then we can go ahead and solve it for v. And when we do, we get the square root of 2 times m2 minus m1 over m2 plus m1 gh, just like before. I'll let it be. I think it's a matter of taste which one that you think may be a more straightforward approach, but it's an important lesson. As long as you don't make any errors of physics or math, any way that gets you there, no matter how ugly, is just as valid as any other way. So whatever way gets you home and makes the most sense to you, that's the way you should do the problem. Okay, in the next series of videos, we'll be extending Newtonian mechanics to look at velocity-dependent forces, and we'll also sit and think a little bit about what if the situation gets so ugly, we just have to throw up our hands in despair and solve things numerically.